Thank you. So let me thank the organizer for the invitation, which I really appreciated. And I'm sorry for not being in Paris with you. I've been following from YouTube here, which actually worked very, very smoothly. Apart from apart from the fact that my 2-year-old son kept asking me why I was all the day on YouTube, he couldn't see Peppa Pig, but jokes aside, so thank you. And I'm gonna speak about some non-local approximation for horizontal perimeter in step 2 Carnot groups. And so let me start by telling you what I want to talk about, like very, very roughly. So the horizontal perimeter is something which has been already discussed in this conference. And the aim of the talk is not really a discussion on the horizontal perimeter. So as you probably all know, I mean, in Subramanian setting, probably appeared first time talking about perimeter in 1982, Pansu as a perimetric inequality. And for general setting over Mander vector fields, the proper class of bounded variation function and the Giorgi type definition of perimeter was settled in a 1994 paper by Capogna, Daniele, and Garofalo. And as I was saying, I mean, I don't want really to touch this notion. So the aim of the talk was rather to propose and to discuss a possible way to give an approximation of this notion, of this horizontal perimeter, by means of non-local object. So what do I mean? I mean, if one thinks that the horizontal perimeter is some total variation of a gradient of a characteristic function, one can think, okay, I want to approximate with some fractional order differentiation of the characteristic function of a set. And so the aim of the talk is to show that we can make it work. We can find a good approximation in a set of Carnot group of step 2 at least for the horizontal perimeter. So this is the plan. So I start talking about the Euclidean case, and this is probably the hard part of the talk for me, because I mean it's a rather recent literature, but it's also very huge. So it's difficult to give a precise account of the literature, but I will try. And then I will speak about our approach, will be a heat kernel approach. And so to both define the semi-norm and for the proof of the approximation. And at some point we should really put the hands on the heat kernel, and that's why we restrict ourselves to the class of step 2 Carnot groups, and I will discuss about this. So all I'm talking about is a joint work with Nicola Garofalo, we've been doing in Padova, and is available on arXiv if you're interested. Okay, so what's a non-local perimeter? So let me speak about the Euclidean setting. I take a set in Rn, a measurable set, finite volume, and so I want to call, I mean, in the literature it is called non-local S perimeter, some Bies of semi-norm of the characteristic function. You can think of this either as a p equal 1 Bies of semi-norm or a p equal 2. And when I write the semi-norm in this way, with these square brackets, I mean this type of semi-norm. So the so-called Aronszajn-Gallardo-Slobodevsky semi-norm of a function. So think p greater than 1 and s between 0 and 1, for example. And this is the Aronszajn-Gallardo-Slobodevsky semi-norm, a very classical object. So there is the appearing of the Riesz type kernel down here. And so why I can define it in two ways here for p equal 1 and p equal 2? Well, this is just by the fact that if I put some characteristic function instead of f, here this difference are either zeros or ones. So if I square it or I don't square it, is the same thing. So this is just the point. And let me stress that here I'm taking s between 0 and 1/2. So why is that? And why this is a fractional order differentiation of the function? So this x minus y to the n, you should see it with the measure as a scaling variance of the measure. So what you end up with is some power p of a increment where downstairs there is a distance to the power s. So when this s is going to 1, you have to think that you are going to really differentiate in some sense. And for s, this s less than 1, you are doing this non-local differentiation. So when did this notion appear? In the literature, I mean, for sure it appeared, and it was, I mean, the beginning of the systematical study of this object, of this Bies of seminorm of the characteristic function as a perimeter, started with a very influential work by Caffarelli, Locre-Joffre, and Savin in 2010. And this started a great amount of literature. And so what did they started doing? They started looking at this notion, look at the first variation, so this so-called non-local minimal surfaces, and a lot of questions. And there is a lot of literature about regularity of this object and classification of this. What they became geometric object, and a lot of literature around this. And so let me also stress that if I take S bigger than 1/2 or equal to 1/2 here, so let me think here at P equal 1 case. So if S is 1/2 or more, here you are doing more than basically one derivative, which is not possible to do. So it's well known that for bounded open set, they have infinite non-local perimeter. So this explains, in fact, the restriction for the range of S. So we have to think that S equal 1/2 is the local case in some sense, which we cannot really touch it because everything blows up. But so when I talk also in the title about a non-local approximation of something local, I mean, I'm talking about some convergence as S goes to 1/2. And so when this approximation of Bies of seminorm literature started, it started since some celebrated works by Burgembre, Dis, and Mironescu in early 2000. And so what did they do? They developed asymptotics of this Aronsain-Gallardo-Solodeschi seminorm, also more general interpolation seminorm, as the fractional order of differentiation approaches the local case. And in this way, they discovered new characterization of classical Sobolev spaces, W1P, or space of bounded variation, as limits of interpolation spaces. And so in their work, they treated both the case of Sobolev, of the Sobolev space, and bounded variation. They left open a question about the case P equal 1, and so the approximation of the BV seminorm, so the total variation of the gradient of the function. And this was settled in higher dimension by Davila in 2002. And this is actually what I want to talk about. So if you take the result by Davila and you specialize to the case of the characteristic function, you are talking really about a convergence of this object that we have defined as non-local perimeter. So the result by Davila gives the following asymptotics for this object. So as S approaches 1/2, this seminorm, this non-local perimeter, if it is multiplied by this factor, which of course vanishes as S goes to 1/2, it goes to the de Giorgi perimeter, up to a dimensional constant. So for me here now, P of E is the de Giorgi definition of perimeter. This holds for any finite perimeter set in Rn. And so again, this goes to 0. So this fractional perimeter is going to plus infinity. Not just that, exactly they balance in such a way you see up to a dimensional constant exactly the de Giorgi perimeter. Okay, so this is really the main focus of the talk. And so what is this constant? So I don't know if you like constant, but this constant can be written as a dimensional constant, can be written with in terms of gamma function, or in a geometric meaning as an average on the sphere of this object here. So this En, it doesn't matter. I mean, any vector you take, you are averaging this linear, I mean, this angle on the sphere. Okay, and so both the Bourgain-Brezis-Mironescu type result, or also this convergence of perimeter attracted a lot of attention, and a lot of proofs appear also in the literature. And concerning the convergence of perimeter, proofs under different point of view were found, for example, by Ambrosio De Filippis Martinazzi or Caffarelli Valdinoci, also other proof under very different point of views. Okay, so this work that I'm talking about stems from started with the question: oh, can we find a sub-Riemannian analog of this phenomenon of approximation of non-local perimeters to the horizontal perimeter? So if we have in mind the fact that they are semi-norm, as I was saying, if you write like this, so it's not hard to think of a replacement of Aronson-Gagliardo-Slobodesky semi-norm in some other setting, because I mean, think you are in a Carnot group, and so we are saying that this dx dy over this power works as a scale invariant measure. So we should think as this as a distance. Let's say we are in a Carnot group to some homogeneous power here, and then we do a fractional differentiation here again with distance to some power 2s. So it's not that we don't have an analog for the Aronson-Gagliardo-Slobodesky semi-norm, but is this going to work or not as an approximation of the horizontal perimeter? And so, for example, I mean, in the literature, Biesov type semi-norm, for different reasons, I mean, mainly for regularity reason, for example, related to Hermander PDs, was considered by Daniele Morbidelli in 2000 or Daniele Garofalo-Neo in 2006. And, but here what I'm talking is, okay, think that you are even in the simplest model case, which is the Heisenberg group. Then we are saying, okay, I have to pick a distance, and then write the Biesov semi-norm out of this distance. So I should take a homogeneous distance, left invariant, homogeneous, and raise it to some power q plus 2s. And so the first question is, which distance should I pick, right? I mean, in the Heisenberg group, we know that there is a sub-Riemannian one, and the Carnot-Caratteudori distance, or we can also pick the distance from the gauge function, which may appear in previous talks, both yesterday or today. And so how can we know which is the right distance, right? And this type of asymptotics can really be affected by this choice. I will come to this fact also later. So what is our approach? So our approach, as I was saying at the beginning, it's a heat kernel approach. And so what is it about? It starts with the following observation, which is, it's mainly computation. So let's say you integrate over time the Gauss-Weierstrass kernel here, which is we all know it's the fundamental solution for the heat equation, which is weighted with this power of T. And this is just the computation. It's very easy that it gives you the risk kernel to this power n plus 2s up to a constant here, dimensional constant. So if one think, okay, I can write the Aronson-Gagliardo-Slobodesky semi-norm with this kernel, and if I do it here and I call it in this way, I put a delta because here I have the Gauss-Weierstrass kernel, which refers to the Laplace equation. So if I write down this type of seminorm, which is the same up to a constant of the Biezov seminorm, the classical Biezov seminorm, then of course I have this relation, and then I can rewrite the asymptotics of Davila with this relation. And so there are two constants which appear. So one is this one, the other one is in the Davila result, what I call K1n, and the gamma function, they do cancel out. Also, any the dependence on the dimension here cancel out, and what it pops up is a adimensional constant. So in other words, this type of seminorm, which is written in terms of the heat kernel, provides a dimension-free reformulation of this convergence result for non-local perimeter. It's just a reformulation. I'm not doing anything here, actually. And maybe this doesn't surprise, because it's one of the many instances of the fact that heat kernel can provide dimension-free things, like if one thinks, of the Stein-Stromberg approach to the dimension-free adimensionality of the constant in the maximum inequality, for example, maybe also even before that, I don't know. Anyway, there are many instances of this back in the literature. This is one more. And, but you see now where I'm going. So suppose now you are in a Carnot group and you take the canonical sub-Laplacian, I denoted by delta G here, and you consider the heat kernel, the one constructed by Folland in the 70s. So the fundamental solution of the heat equation here on the Carnot group. And I want to fix this notation. So PTU for U in LP is on the group is the group convolution against this kernel, against the fundamental solution. And with this notation, I can write the seminorm out of the heat kernel. So for S between 0 and 1 and P greater than 1, one can define the horizontal Biezov space. I define it in this way as the collection of functions U in LP, such that this seminorm is finite, okay? And then have in mind what I've seen in the Euclidean case, what we're proposing here is the following definition for horizontal S perimeter, which is that if you take S between 0 and 1/2, we say that the measurable set has finite horizontal S perimeter if the characteristic function is in this Biezov space that I just defined. And we define the horizontal S perimeter as this seminorm, as this interpolation seminorm written in terms of the Folland heat kernel. Okay, so with this Gothic P notation, I want to define this non-local notion of horizontal perimeter. Okay, so what is the result that I want to discuss today is this one. So if you suppose that the Carnot group is of step 2, then we have the exact asymptotics of this non-local horizontal perimeter to the horizontal perimeter, and the constant here again is a dimension-free constant, and also is the same dimension-free constant which appeared before, the 4 over square root of pi. So in my notation, this Gothic PH without the S is the horizontal perimeter. Okay, so it's already been defined the conference, and I want to go through this. Just recall for future purposes that on smooth sets, is already being recalled in previous talks. On smooth sets, you have a density in the surface measure, in front of the surface measure, and this density measure, it's the norm of the projection of the normal on the horizontal distribution. So it feels if you are characteristic or close to be characteristic or not, in some rough sense. So what we are saying here is that, very, very hand waving, with the heat kernel somehow sees a way as S approaches 1/2 to see this density, to recognize this being characteristic or not characteristic with this density. I will come back also to this at the end. Okay, so some comments are in order. So I don't want to make you think that this notion of Biezov interpolation spaces out of kernels, out of heat kernels, for example, is a new appearance in the literature, because it's not. So, for example, what as far as I know, it appeared in some works in 1964, 1965 by Tableson. So it was for different purposes. Actually, I think for some harmonic analysis purposes. And he both considered the Gauss-Weierstrass kernel, so the heat kernel, and also the Poisson kernel, and he considered interpolation seminorm with respect to this kernel. And actually, can be even more. It's more rich, the family of interpolation spaces constructed via kernels, via heat kernels. For example, I can consider this type of seminar. Now, because in this, the heat kernel, there are two things. One is space, one is time, and one can think to mix the LP spaces. So one can think that you can write a LQ norm in time. This is invariant measure in time, LQ in time, of something which is an LP in space, weighted by S. And so classically, these interpolation spaces are Biezov BPQS spaces. And what I fixed before with this Gothic P is the choice Q equal P, basically, right? So if you Q equal P, here you have 1 over P, and here you don't see anything. And this is the definition I fixed before. Okay. And so one can make many choices. And why did we fix basically Q equal P in the previous definition? Is exactly because we can recover the Davila result with that seminar. Okay, but for example, different choices. In the case Q equal infinity, I mean this LQ becomes a sup in time. Supremum in time. Biezov spaces in a very general class of Dirichlet spaces, a heat-based notion of Biezov space was considered in recent works by Alonso Ruiz, Baudouin, Chen, Rogers, Chamungalinga, and Teplayev. And actually, the case Q equal P, as in the presented work, and we considered this in some recent work with Garofalo and with Buzugin Garofalo, relative to heat-based notion, relative to the heat kernel of some Kolmogorov type operator, which appear in kinetic theory of gases, and which are some operators which have constant coefficient in the second derivative and are linear in the first derivative. And okay, actually, we started from this type of operator, and then they will come back again, so I will come back to this. Okay, so last comment. So if we fix the context of Carnot groups, the one result I know about some convergence as S approaches 1/2 or some type of non-local perimeters is this one by Ali Malau and Andrea Pinamonti in 2019. And they showed, okay, if you fix any homogeneous symmetric norm, so any, homogeneous symmetric distance, or also quasi-distance, I think, and you write down the Ries-type definition of Biezov seminorm, so what I was telling before, some distance to the power Q plus 2S. So you have this type of result. So if you multiply by 1 over minus 2S, you see qualitatively the perimeter in the limit, but you miss the exact asymptotics in some sense. And so what I'm telling you, the result I'm presenting, actually is like saying that with the heat kernel, in some way we have detected the right distance in order to have this exact asymptotics. Because of course, this is, it doesn't depend really on the distance, right? Because they are equivalent, all the homogeneous symmetric distances, up to constant. And then you are changing constant here. So in some sense, we are detecting the right distance, which is not really a distance if you write in this way, our way, the heat kernel way, to write it, because it becomes sort of S-dependent distance. And as S approaches 1/2, this S-dependent distance goes the right way and goes to the horizontal perimeter. This is what we're saying. Okay, so let me say something about the proof. And so the proof is divided in two main steps. The first step allows to transfer the convergence in S, as S going to 1/2, in a convergence in time, as time going to 0, which we like more. And so what we have, in fact, is that the lim sup of this expression and the lim inf can be bounded in terms of this expression. So the L1 norm of Pt of the characteristic function minus characteristic function scaled in this way, 2 over square root t. So the lim sup is bounded by the lim sup of this, and the lim inf by the lim inf with the same constant. Okay, these two estimates actually they hold true in a wide generality. You don't even have to be in a group. It's just under my assumption on the semi-group. These proofs work. And but I mean later the next step, the fact that we are in a Carnot group, and even Carnot group of step 2 plays a big role. Okay, so up to here, we have a general result that tells you that we can transfer these convergences in S to a convergence for small time asymptotic. So it becomes, the question becomes, can we say something about this limit as t goes to 0? No? So the second step concerns exactly the understanding of this limit. Okay, and okay, very good. So it turns out that such a quantity, let me call it functional, such functional is well studied. And why is that? Because it was relevant in the heat semi-group approach by Ledoux to the isoperimetric inequality, and which works in some different settings. And so it already appeared in the literature. And moreover, it is also very much connected with an alternative definition of perimeter, which is also due to the Giorgi, the classical perimeter, as this type of object. So you have your characteristic function, which is, I mean, we have to imagine a jump function. You run the heat flow, it becomes a smooth function. You can differentiate, you can take the gradient and measure it in L1 and see what happens at t goes to 0. And this is actually was probably before the BV definition of the Giorgi. And these two definitions, at least in classical setting, they are the same. And okay, and so this is also related to a previous talk today, like, because this is a sort of in that notation, a sort of heat content, right? I mean, there was a bounded set, and there was an initial boundary value problem on a cylinder. So bounded set close R is time. And so there was the solution, and there was an asymptotic that if you subtract the volume and you look at the asymptotic in square root of time, at the first order you see perimeter, and this is what we are talking here. So, but this is a global problem. So you have your set E, you look at the characteristic function, and you run the heat on the whole space. Okay, so it already appeared, this notion, in the literature. For example, what happens in Rn? In the case of Rn, there is a very nice paper by Miranda, Pallara, Paronetto, Preukert in 2007, and they proved that they proved this limiting relation for the Euclidean heat semigroup. So for any finite perimeter set E, this limit is the Srgi perimeter up to this constant. Okay? I mean, if you think to this is the definition. This is another way to say perimeter. One inequality is sort of Poincaré inequality, and they are actually saying it's true also the other inequality, the one from below. Okay, so let me stop here for a moment, because what we are saying here is that if we combine the asymptotic estimates I showed you 3 or 4 slides ago with this result by Miranda, Pallara, Paronetto, and Proikert, we actually retrieve the result by Davila. In some sense, is a new sheet-based proof of the convergence result for non-local perimeter, right? Because we start from this semi-norm, and we know now that this limit exists, so the lim sup and the lim inf, they coincide, and the constant here, they match perfectly, and they should, and this was Davila result. Okay. So what about in Carnot groups? In Carnot groups also, this functional, and since appearing in this Ledoux works, I mean, let me call Ledoux type functional, was considered in the context of Carnot groups, and by Bramanti, Miranda, and Pallara in 2012, and with what purpose? With the purpose of, let me go back, with the purpose of giving this type of heat semi-group characterization of the horizontal perimeter, and some characterization of BV function in Carnot groups, heat-based characterization of BV function, and they face the problem to understanding what is the limiting relation of this Ledoux functional. And what they proved in this paper in 2012 is that for any finite horizontal perimeter, if the Carnot group is of step 2, okay, and let me identify the group with the Lie algebra. This is the splitting of the Lie algebra. One has that this functional, as the limit exists, and they represented the limit in this way that now I'm going to describe. So up to 4 is the constant. So here we have in this weird way, I denoted the horizontal perimeter measure, and we have a density here. So the horizontal perimeter measure, if this density is not there, this would be the perimeter, right? So we have a density, which can be a problem, and this density can be written in terms of the heat kernel. So actually, this density depends on a horizontal vector, and in which way it's an integral of the heat kernel at time 1 on a hyperplane, on the vertical hyperplane. So on the hyperplane which is orthogonal to this horizontal direction here. Okay? So what we can prove and what we realized is that, okay, this density here, which in principle, as they wrote it, that could depend on the group and on this horizontal direction, it's actually universal. So it's 1 over square root of 4 pi. So for any horizontal direction and for any step 2 Carnot group. And so with this lemma, we are done, because then the constant, they just match. Okay? So as I was telling before, using the result in Rn, we can do the same here in Carnot group of step 2 if we know that this density is this precise constant. Because in this case, for any finite perimeter set, we know that this limiting relation is this constant times the horizontal perimeter, but this is our convergence of non-local objects. Okay? So if we realize that this is this precise constant, the proof is finished, is complete. And how do we prove this? Well, we proved it basically by brute force. And so let me start with the case of the Heisenberg group. So let me fix the notation. So Z or zeta are the horizontal variables, sigma or tau are the vertical one. And this is the group law. J is the complex rotation. So the heat kernel is given by this formula, which is familiar to a lot of people in this conference, and which was found by Ulanicki and Gaveau. And so if you look at this formula, and if you recall what was phi g of nu, which was an integral of some hyperplane of this heat kernel, is not difficult to recognize that this does not depend on this horizontal vector nu, basically because of the invariance here with respect to rotations of this horizontal part, this norm of z squared. And so it's very easy to recognize that it's independent in the Heisenberg group, or even in H-type group. It's the same. It is independent on the vector nu. To identify which is the constant, I mean, when it's explicit, one should make additional work. And this is what we can do, for example. But so let me say what is the general case. So now I'm going to introduce some notation for the step 2. They already appear, also very similar notation in the conference. So for me, we have a Carnot group of step 2. We have the splitting of the algebra. So M is the dimension of the first layer. K is dimension of the second layer. And so again, this is the notation for the variable. Z is in Rm and sigma in Rk, vertical sigma and horizontal Z. So, and there is this J map from the second layer to the endomorphism of the first, which is defined like this. And the fact is Carnot group make this map injective. And we consider the group law coming from the Becken-Campbell-Hausdorff formula. And this map J, of course, from this definition is Q-symmetric. And I want to consider this symmetric endomorphism. So J transpose J, or minus J squared. So in my notation, A of sigma is this symmetric non-negative endomorphism. And so since it's non-negative, is well defined, this non-negative element, this square root. And more notation, if you have a matrix, think of symmetric matrix M times M, I want to use this strange notation, J of the matrix. And this is just this function, x over hyperbolic sine of x, applied to the symmetric matrix. So if it's an analytic function, you can think you have the analytic expansion and you use the power of the matrix to define it. And similarly for the cosine. So if I have this matrix notation, the heat carrying Carnot group of step 2 can be written in this integral formula. Okay, this is very similar to the case of the Heisenberg group of H-type group, right? Because here we have some lambda over hyperbolic sine lambda to some power, and here we have lambda over hyperbolic tangent, if you want. And the heat kernel in Carnot group of step 2, it appeared in a work by Srgi in 1979. And the integral expression, of course, was an integral expression and was a slightly different version than this one. And let me just tell you, maybe you are very familiar with this fact, but so actually Srgi, what he did was, okay, in free Carnot group of step 2, there is this formula, the integral formula for the heat kernel, and then there is a way to lift any Carnot group of step 2, actually, when a very explicit lifting, to a free one, to a free Carnot group of step 2. And so in the integral formula appearing there, you have also the integral on these additional variables coming from the lifting. this type of integral expression, which worked very well for us for the purpose of computing that function, the density phi that I was telling you before, is actually in the same spirit of formula which were written and used in works by Müller and Ricci, and also Martini-Müller. So it's not something new, this type of integral formula. Maybe also you are, I mean, in this audience, there are a lot of people expert in it-kernel asymptotics for sub-Riemannian settings. So maybe you already are familiar with this. So in a recent note with Nicola, we derived we did a new derivation of this type of integral expression. And also Nicola, in his talk yesterday, was talking about this. And this derivation, what we feel is nice, maybe you can tell if you know more literature than I do. It's a derivation that comes from first principle in the sense that there are no a priori answers about cylindricality or something like this. And is by means of pure PD tools, actually, it highlights a relation with an Ornstein-Uhlenbeck type operator that I want to describe in 2 slides. So the canonical sublaplacian in my notation can be written. So, and of course, this is classical. One way to, this integral expression comes with a Fourier transform in the vertical variable. And if you do this, you are led to consider a Cauchy. If you want to find the kernel for heat kernel for this operator, you're led to consider to solve the Cauchy problem in the Fourier variable here. So Z is fixed and sigma became lambda. And now from now on, I consider lambda fixed. So this is classical. And there are 2 things that I don't like very much in this operator. One is this complex drift. And one is the fact that the 0 order term, which is kind of harmonic oscillator, is not really a quadratic thing. I mean, in the Heisenberg case, it is a quadratic thing. But in general kernel groups, I mean, you can have a big kernel also in J. This A is the square root of J square. So you can have a big kernel. So one can guess, actually, one can do here an ansatz, which is very natural, maybe. So if you are radial, maybe you are killing the first order thing. If you split your matrix J of lambda with basis with a big kernel, and then some Heisenberg, some even blocks with some Heisenberg type thing, which you know the heat kernel of, you do very, very, very natural ansatz. But let's say we don't want to do it. So if we don't want to do it by means of 2 change of variables, we actually, which one is a complex rotation, which kills the complex drift. The other one is a Gaussian-like change of variable, which transfer the term, the 0 order term of the harmonic oscillator in a first order term. We end up looking at a Cauchy problem like this, where you have second order part here is constant, and the first order part here is linear, which is basically the same type of operator like the one in kinetic theory I was talking before. So when we arrived here, we were very happy because we know very well what is the fundamental solution. Actually, I learned how to compute the fundamental solution once you are here in a celebrated paper by Armander, the one by the higher polyticity paper by Armander. And this is given very, very explicitly. And actually to do it is very simple. You go in Fourier, you do, it's a very simple application of characteristic method. And then you end up with this Gaussian when you go back from the Fourier side. And the covariance matrix in the exponential is given by this expression. So to answer to a question raised by Roberto Monti yesterday, actually in the talk by Garofalo, was well, in this interpretation, where do we see the hyperbolic sign? Where we see them here. Because if you conjugate this covariance matrix, you end up with this expression, this series, and it's easy to see here like a hyperbolic sign with 1 less power. So this is like the series of sin h of x over x, which is the inverse of the function j I defined before. And then you go back and you retrieve the heat kernel. So I'm finishing So it was very useful for us, this representation, to prove by brute force, I was saying, that this function is this exact constant. And so the final comment, so the proof by Bramanti, Miranda, and Pallara, actually it's a sort of the geometric measure theory proof was different from the Euclidean one before by the authors I cited. And it relies on a blow-up procedure for the reduced boundary, and they make a big use of the rectifiability result of Franchi, Serappioni, Saracassano in step 2 kernel groups. And that's why it appeared that function phi, the function phi was an integral of a vertical hyperplane. And the vertical hyperplane is what you see in this blow-up procedure, basically. And actually, our intuition that the heat kernel might save our day, it was different. Actually, we didn't know about this result by Bramanti, Miranda, and Pallara. So when we started to see as intuition how the heat kernel sees the right density, which is inside the horizontal perimeter, it can be thought like this. So this Leduc functional is really it's defined through this L1 norm, and you can, if suppose E is smooth, you can represent this as this integral. So you have an average in time and an average on the boundary of something with the heat kernel and some horizontal normal computed in G and G prime. And what we were able to do is, in order to see the density in the horizontal perimeter coming out, was to prove an asymptotic of this form. So what is inside one of this integral here is really converging to the density. So in some sense, it's different from their approach, where they want to see up to for almost every point, they do this blow up and they see the non-characteristic case, so the vertical hyperplane. Here, actually, it make you see that, okay, the heat kernel really seems to not care, at least for smooth set. For C2 smooth set, you can see that you can be characteristic, non-characteristic, close to the characteristic set, and still you see this density in this small time approximation. And that's it. So thank you very much for your attention.
Thank you. So are there any questions on the talk? Yes.
Hi, Giulio, it's Valentina. Ciao.
Hi.
So I was wondering if you, say in your proof, you only use like small time asymptotics or not. So maybe I missed this point. Because in this case, I was wondering, so due to the heat kernel asymptotics for small time, this thing might work also for the Carnot-Kara-Theodori distance. So I don't know, what do you think? Can it work for the CC distance instead of using these heat kernels?
Yeah, I see what you mean. It could. Well, I'm not sure it does, but it could. I mean, I'm not sure it does in the sense that you are averaging, this functional in time. So you have, there are these small time asymptotics, and you have to wonder that when you are moving points, and this non-local type definition, really you're averaging points, and you want to see if this averaging works well with if there is enough uniformity in average to go, if you use the asymptotics with respect to the Carnot-Kara-Theodori distance. So it could, but I'm not sure it does.
Just to say thank you. Okay, thank you very much.
Any other questions? Okay, so let's thank the speaker again.
Thank you very much.